In this manuscript, we elucidate a previously unharnessed phenomenon arising from the seasonal variation of our thermally radiant environment and the differential transmittance of the atmosphere towards the sky and within terrestrial environments. This enables selective long-wave infrared emitters on vertical facades of buildings to achieve a passive radiative cooling in the summer and heating in the winter, relative to traditional broadband emissive building materials. To our knowledge, this work is the first to elucidate the mechanism of this novel passive radiative thermoregulation. Besides describing the mechanism, we experimentally verify this effect and show a range of scalable and common materials which can harness it, some for the first time. And using building energy models, we show how it can lead to significant and untapped energy savings comparable to painting dark roofs white. Our work also deals headfirst with a fundamentally important but overlooked issue in recent radiative cooling research, namely that for vertical surfaces, typical radiative coolers are overwhelmed by terrestrial heat and has large implications for cooling walls, windows, and human beings. We introduce our idea with the well-known phenomenon of radiative cooling, which allows sky-facing thermal emitters on Earth to lose heat through the long-wave infrared transmission window to space and passively cool to subambient temperatures. However, research in the past 6 or so decades has dealt mainly with sky-facing surfaces, with vertical surfaces and the effect of seasonal terrestrial irradiance on them not considered. However, buildings have a significant fraction, often the majority, of their surfaces vertical. For vertical surfaces like walls and windows, the thermal environment is much more complex because now the terrestrial environment covers half or more of the field of view. In the summer, when the earth gets warm, this hot environment counters the cooling effect of the sky, something that is not considered in radiative cooling literature. What is more, the atmosphere here plays a subtle but unhelpful role. Towards the sky, it is thick and thus transparent only to narrowband radiative heat loss in the long-wave infrared, shown in blue. However, between terrestrial objects, it is thin and thus transparent across the thermal wavelengths. Thus, the terrestrial glow that hits buildings in the summer is broadband as shown in red, and when one compares the red and the blue for humid and dry conditions, it is clear that the terrestrial glow negates or even reverses radiative cooling to the sky. In the winter, however, the opposite happens. Now the ground tends to stay cold most of the time, meaning that buildings lose broadband heat, leading to overcooling. This is important because traditional building materials and scalable radiative coolers reported so far are all broadband emitters and absorbers, whether we are talking about asphalt, wood, concrete, paints, and so on, or recently developed radiative coolers like super white coatings, polymer composites, or thermochromic windows. All of these designs may suffer from this undesirable summertime broadband heating and wintertime cooling, making them unhelpful when it comes to vertical facades. However, a solution to this problem is inherent in the atmospheric bias that we mentioned earlier. Since skywards heat loss is narrowband and terrestrial heat gain in the summer is broadband, if we can use a selective emitter that restricts heat flow only to the long-wave infrared window, we can filter out much of the broadband heat gain without cutting down on the heat loss to the sky. This enables a large relative cooling effect. And in the winter, when the ground is cold, the same emitter cuts down on broadband heat loss, enabling a relative heating effect. So through this insight into the differential atmospheric transmittance and seasonal variations in the terrestrial environment, we show that selective emitters can attain a novel, passive, and seasonal thermoregulation relative to broadband emitters on buildings. And this happens without any energy usage, CO2 emissions, or phase changes that characterize electrochromic or thermochromic designs. In other words, we show a static design that achieves a radiative thermoregulation as the world changes around it. This is exciting because the seasonal cooling and heating is significant. As shown in this plot, during summer days, when the air temperature and the relative ground temperature are both high, the relative cooling potential of selective emitters can be as much as 50 watt per meter square. and in the winter when the ground is mostly cold, it can be as much as 20 watt per meter square. Please note that these cooling potential differences are by definition for broadband and selective emitters held at ambient air temperature. Building surfaces, due to their contact with indoors, may be considerably colder in the summer and warmer in the winter, which would heighten these values. We also show that for urban heat islands, where a large fraction of the view are warm buildings, the relative cooling effect increases. That is, this mechanism works in both open and congested environments. We also show that this effect can be achieved by super white, moderately white, transparent, and dark surfaces. This means that our design can be useful for a range of building surfaces ranging from walls to windows. To verify if our approach is sound, we performed a number of experiments in warm and cold conditions in Los Angeles and over different durations. As a selective emitter, we used polymethylpentene, and as the broadband emitter, we used PVDF. The experiment that illustrates the concept was done on a rooftop on a winter night in Los Angeles. Because of radiative cooling, the roof had cooled to 5 degrees Celsius or so below the ambient air temperature, representing a wintertime scenario. However, the pool, which was maintained at 11 degrees Celsius above the ambient temperature, also allowed us to mimic a mild summertime scenario. Initially, the PMP and the PVDF were placed facing the cold ground, and what we saw was that the PMP selective emitter, which prevents broadband heat loss to the ground, was 0.21 degrees Celsius warmer than the PVDF over a half-an-hour period. However, when moved to face the warm pool as shown here, the PMP became 0.16 degrees Celsius cooler and stayed so for an hour, in line with theoretical predictions and therefore verifying our theory. We did further experiments across summer and wintertime conditions, and what we saw that was in summertime conditions, the PMP selective emitter was cooler than the PVDF broadband emitter, and in the winter, the PMP was warmer or at the same temperature as the PVDF. All these results were theoretically consistent, which lent strong support to our proposed mechanism. And while the temperature differences here may look small, we stress that they are entirely expected for radiative cooling experiments that are vertically oriented, unlike for sky-facing cases. It is important to note that heat flows in this experiment, which uses the same setup as those in typical radiative cooling demonstrations, are different from what buildings experience. What our experiments do is validate the theoretical model as we intended. And this, in turn, implies large differences in heat flows through selective and broadband emitters. We verified this by doing differential power flow experiments on a winter night. In the experiment, we supplied both emitters with the same power and compared the difference in radiative power as a function of the emitter temperature. Accounting for experimental uncertainties, the power flow differences were again consistent with the theory and significant. So, our theory holds, but what does it mean for buildings? To estimate the benefits, we created a detailed heat transfer model that simulates building heat flows in desert and highly humid scenarios in both peak summer and peak winter, based on weather data for the southwestern US and the Indian subcontinent. As facades, we chose an R13 insulated wood facade commonly used in the US, a single layer brick wall predominantly used in buildings in South Asia and similar subtropical regions, a single pane glass window which is the most commonly used transparent facade in the world, and corrugated metal sheets used as walls in resource-poor settings. These choices represent a major subset of building facades used worldwide. And what we find is substantial energy savings in both summer and winter. The bars here show the kilowatt hour per meter square per day of undesirable heat gain or loss avoided with our approach for the different facade types that we chose. Across the board, the savings are often comparable or several times greater than what we get when dark roofs in American houses are painted white, which is already widely accepted as beneficial and shown with dotted lines. The benefits are particularly large for low insulated facades like brick walls and windows, which are common in large parts of the world. While the benefits are the highest for ideal selective versus ideal broadband emitters, we see that the savings persist even when the facades absorb sunlight, like typical white paints. Indeed, the solar absorptance can be 0.5 for directly sunlit facades or even higher before the benefits of our approach disappear, meaning that we can use super white surfaces or colored surfaces as well. We also find that the PMP used in our experiments, despite being unoptimized for cooling, can offer significant benefits over white painted facades. This shows that even readily available materials can harness this effect to yield considerable benefits. Crucially, these savings are additional to the benefits of solar reflectance, which means our approach keeps the benefits of traditional high albedo approaches and offers substantially more. Moreover, the values we see here are calculated on a per unit area basis. In reality, the wall to roof area ratio can be quite large, especially for tall buildings. When all of these are considered, we estimate that for moderately sized buildings, our approach can reduce CO2 emissions on buildings by as much as 0.1 to 5 tons per year and save $50 to 1000, depending on the facade type. These are very large and significant values and comparable to painting roofs white. And these are complementary to existing methods, and most importantly, they are completely untapped. Given the novelty and the large energy savings and emissions reductions enabled by our approach, we surveyed selective emitters that can harness this effect on buildings. Given the urgent global need to mitigate and manage heat across socioeconomic settings, we did not necessarily aim for innovative materials, which may have a limited reach and can take years to be used on buildings, and focused instead on materials that are simple and commonplace. Towards this end, we highlight prior materials like polymethyl pentene and polyvinyl fluoride, which were reported as selective emitters in the 70s and 80s. PVF is actually currently made at scale for roofing applications and could be used on vertical facades as well. Likewise, silicone and acrylic, which we and others have reported as selective emitters, could be painted onto metal facades to give selective emittances. Our search also yielded novel insights into globally ubiquitous materials. For example, we show that polypropylene, which is produced in metallized forms at scales of around 1 billion meters square per year, is perhaps the most common selective long-wave infrared emitter on Earth, and quite a good one. Variants of polypropylene are already used as roofing membranes, and the spectrum you see here is of polypropylene sourced from plastic waste. So these results alone are very significant for the radiative cooling field. We also report a novel material design, ceramic tiles made from materials like alumina, whose porosity and whose bulk phonon band gap can make them novel metal-free selective emitters, something that to our knowledge has not been shown before. All of these materials have moderately good selectivities relative to existing building envelopes and can come in white, transparent, colored, or metallic appearances, and can be applied using a variety of established techniques on walls and windows. And most importantly, these are inexpensive, readily available, and in some cases, readily available for use in buildings. And these materials, even though they are unoptimized, actually have a pretty good selectivity, and they could be optimized even further. So in showing all these possibilities, our work opens an exciting avenue for both immediate use and further development of selective long-wave infrared emitters. So in summary, we have shown a novel seasonal and passive radiative thermoregulation which arises from the differential transmittance of the atmosphere and the seasonal variations in terrestrial environment, which vertical facades of buildings can achieve by using selective long-wave infrared rather than traditional broadband emitters. This work is uniquely comprehensive in that it introduces a new insight, perhaps the first in recent memory, into our radiant environment, experimentally validates it, models its impacts on buildings to show large and untapped energy savings and emission reductions that are complementary to albedo-based ones, and shows a wide range of readily available materials that can be applied to buildings to harness this effect. As such, we believe that this work represents a major milestone in radiative cooling and building energy research. Furthermore, the significance of our work goes beyond buildings to vehicles and radiative cooling textiles as well. On the latter, major works which report broadband designs have curiously not considered terrestrial heat gain and loss, which means that in real operating conditions, they may be ineffective and perhaps counterproductive at cooling. In showing materials like polypropylene and PMP from which fabrics can be made and which can cool even under the Earth's glow, our work provides a fundamental advance in this regard. Thus, our work is likely to have a wide-ranging impact for broader field of radiative cooling as well. Thank you for viewing this, and we hope that you will find our work meaningful.